temperature can help the police catch criminals.
We have a system on board the aircraft called forward-looking infrared. It doesn't come cheap. It's very expensive. But what it does enable us to do is to turn darkness into daylight. We're able to watch an onboard TV monitor, and people, whether it be in pitch black conditions, stand out to us like lighthouses.
Andy, we're going to a car chase. It sounds, I don't know what they're chasing. It's very fast. 99 Channel 2, we're overhead this pursuit.
Slung below the helicopter is a special thermal imaging camera.
Right, get ready for a bailout here.
Instead of seeing light, it sees heat.
Still moving, Dave. 992 units, we've got the bailout, the garage.
High temperatures, like a person's body, look black. The cooler surroundings are shades of grey.
We've got 2 suspects out at the moment. The police officers, that's 2 of them. That's definitely 2 of them.
Right. They've got 1 arrest out the other side.
Have they? So they've got 3 then?
Yes.
Oh, they've got 4 now. 4 out of 5. 99, that was received. So you've got 4 out of 5. I beg your pardon. In that case, I think we will call that a result and resume.
A job well done thanks to thermal imaging.
Well done.
Being able to see temperature differences makes an ordinary supermarket look completely different. This camera produces a computerised image that makes hot things look yellow and white, cold things look blue or black. This boy's ears and nose are slightly cooler than the rest of his face. Why does a hot cup of tea leave a yellow mark on the tabletop? What happens to your face when you eat an ice cream? Out on the street, car engines are much hotter than their surroundings. Warm hands on a cool wall can also leave their mark. This guy has been sitting in a hot steam room for several minutes. What's going to happen when he steps into a cold shower? The warm yellow becomes a cool blue. We use our skin to feel how hot or cold something is, but just how good are we at judging temperature? What about this swimming pool?
I think the temperature of the pool's about 17 degrees.
I think it's about 30 degrees. I think about 25 degrees.
17, 25, 30, it's all guesswork.
Today's temperature in the pool is 31 degrees Celsius.
So none of them were right. Our skin isn't able to measure the exact temperature of anything. All it can do is recognise temperature change. To see what I mean, take a couple of bowls of water and 2 investigators. The bowl of water on the left is warm, the one on the right is much colder. They each keep a hand in the water for 5 minutes. Then it's time to introduce 2 identical cans of drink. The temperature of the cans is midway between the 2 bowls of water, so how will our investigators react when they pick them up?
This can feels warm.
But this can feels cool.
Hang on a minute. If the cans are both the same temperature, how can one feel warm and the other feel cool? Try it for yourself and see if you can work it out. Body temperature is a good indicator of how healthy we are. In the past, doctors placed their hand on a patient's forehead to check if they were ill. But they often got it wrong. They needed a thermometer, a tool to measure temperature accurately. One of the earliest thermometers would have looked like this. It's made of a glass bulb with a long, thin neck. To construct it, the bulb needs warming. Then the end of the long tube is dipped into a flask of coloured water. As the bulb cools down, watch what happens to the level of the red liquid. It rises up the tube. Cool it even more and the water continues to rise. Warm the bulb and the water level falls. It's all to do with the fact that hot air takes up more room than cold air. Imagine you can see what's happening to the air particles. As the particles get warmer, they begin to move faster, they're gaining energy. The particles push each other further apart and the air expands. Because the air takes up more space, it pushes the liquid down. When the air cools, the opposite happens. The particles lose energy. They move around less and the air contracts. As the space they take up decreases, the liquid rises. Over 350 years ago, the air thermometer was the only instrument available to doctors. To measure body temperature, all they had to do was find a way of putting the bulb in the patient's mouth. A smaller bulb was the answer. The doctor measured their own temperature first, marking the level of the liquid, before popping it into the patient's mouth, something you never dream of doing these days without thoroughly sterilising. This way, they could see if the patient's body was hotter or colder than theirs. In the 1600s, anyone interested in measuring temperature made their own device. They came in all shapes and sizes. But because there was no standard design, it was impossible to compare the readings of two different thermometers. What was 6 on one might be 16 on another. Scientists needed a standard scale. More modern thermometers use a liquid in a sealed glass tube. This time, it's the volume of the liquid that changes with temperature, not the volume of air. To work out a standard scale, you first need a fixed low temperature, like the melting point of ice. The red liquid contracts, so the level in the tube drops. Once the liquid has settled, the low point is marked. Then you need a fixed high temperature, like the boiling point of water. This time the red liquid expands, so the level rises. Once the tube is marked with a low and a high point, you can divide the space between them into equal parts. The scale used by scientists today was the one invented by a man called Anders Celsius. 0 is the low point, the temperature of pure melting ice. 100 is the high point, the temperature at which water boils. The distance between is divided into 100 equal parts. This same technique is still used to make thermometers today. At the Zeal factory in London, each thermometer is individually made. bulb is fitted, then the tubes are filled with a coloured liquid. A low and high temperature is marked on each by hand before adding the scale. It's a painstaking and time-consuming process. But not all thermometers look the same. A thermocouple thermometer, like this, can measure the temperature of red-hot metal. Or extremely cold liquid nitrogen. There are thermometers everywhere. When is it important to be able to measure temperature accurately? You can measure the temperature of anything. It tells you how hot or cold something is. Temperature is all to do with energy. To take a closer look, we're going to use a strawberry milkshake and a hot chocolate. The temperature of the strawberry milkshake is 2.1 degrees C. The hot chocolate is 44.9. Imagine you could see the tiny particles that make up the milkshake. Temperature is a measure of their movement energy. Each particle is moving slowly, so the temperature of the milkshake is low. The particles in the hot chocolate are moving much more rapidly. The movement energy of each particle is higher, which means the temperature of the hot chocolate will be higher too. But surround the hot chocolate with the cold milkshake, and what will happen to their temperatures? A speeded up sequence using a thermal camera allows us to watch the change. Eventually, everything begins to look the same colour. The milkshake and hot chocolate and their surroundings become the same temperature. What can you now say about the energy of the particles in each drink?
Miriam!
Oh, goody aunt.
What are you doing?
Lottie and Nerd, I was just relaxing. I'm very tired.
Tired? Do you mean you're tired? I'm the tired one. I've been looking all over for this lot. I'm all hot and flustered now.
Are you? Bit hot, bit tepid, bit warm.
Yeah.
Bless you. Well, I think I can help.
Oh, how so, little chum?
Oh, I am petite. No, I'm going to make ice cream.
Ice cream?
Yes, just the thing to cool you down.
Well, where is it?
I'm going to make it.
Where?
Here.
When?
Now.
Well, how long will it take?
30 seconds.
30 seconds?
Yeah, no, I just not. Look, pass me the stuff, I'll show you.
Oh, well, what do you need? Oh, chocolate, probably.
No, no chocolate. Oh. Now, first of all, I need some custard.
OK, some custard.
It's lovely, thank you. A little bit of cream.
OK, a little bit of cream.
Fold that in. A few strawberries.
Ooh, there you go.
Thank you. And a spoonful of sugar.
Spoonful of sugar.
That's it. And then there's a secret ingredient.
Oh, what, like secret chocolate,
no,
for example?
No, chocolate.
Oh. Well, chocolate or not, I'm not convinced by this 30-second theory of yours.
Look, you can trust me on this one. OK, and put these on.
Ooh.
There you go.
Must be strong ice cream. So what is this secret ingredient, then?
Well, it's got a code name, which is N2.
Oh, cool.
It is cool, actually. No, actually, it's really very cool. Shall I tell you how cool it is? It's minus 196 degrees Celsius worth of cool.
No, I'm sorry, you've lost me.
No, sorry. No, it's just to say that the secret ingredient is very cold, because it is liquid nitrogen. Yeah. Now, you stir. I'm going to pour.
OK.
OK. Nice stirring action.
Like that. Fantastic.
Keep stirring.
OK. I'm keeping stirring. Yes, something's definitely happened. Wow. Well, bloomin' hammer.
You see? Ice cream in 30 seconds.
That's amazing!
Yeah, well...
Needs chocolate.
Oh, she never gives up. But there is another quick and easy way to make your favourite ice-type refreshment.
What do you need?
You need the same ice cream mixture, 2 tubs, some ice, some salt, and...
Some chocolate! Ow!
No! Will you give it a rest about the chocolate? No, you don't need chocolate. You need a shaking action. A shaking action. Oh. Yeah. You see, what you do is you have to put the ice cream mixture in the small tub. Mm-hmm. Put the small tub in the large tub with some ice and some salt. Okay. Put the lid on and shake.
Shake?
Yeah.
Okay.
Shake for 20 minutes.
20 minutes?
Yeah. And begin.
And there you have it. Perfect ice cream in just minutes.
So, how is it?
Needs chocolate.
Now for the explanation. The particles in the liquid ice cream mixture have much more energy than the particles in the ice and salt water mixture. Once in contact with each other, the energy is transferred from the warmer substance to the colder substance. Shaking helps this transfer of energy. It increases the contact between the salty ice and the ice cream mixture. Eventually, the ice cream and the icy salt water will both be at the same temperature. The icy salt water is still below 0, which is why the ice cream in the middle has frozen. A similar thing happened with the liquid nitrogen. Energy was transferred from the warmer ice cream mixture to the much cooler liquid nitrogen. The nitrogen changed into a gas and disappeared into thin air. Even cold things have energy. So how does the amount of energy in a small bowl of ice cream compare to the amount of energy in a large tub of ice cream? The ice cream in both the tub and the bowl are at the same temperature, so all the particles have the same amount of energy. But if the portion in the bowl is smaller, there'll be fewer ice cream particles. The large tub contains a lot more, so the total energy of the big portion will be far greater than the total energy of the smaller portion. So which has more energy this time? A cup of water or a swimming pool full? This camera produces a computerized image that makes hot things look yellow and white, cold things look blue or black. This boy's ears and nose are slightly cooler than the rest of his face. Why does a hot cup of tea leave a yellow mark on the tabletop? What happens to your face when you eat an ice cream? Out on the street, car engines are much...
Darkness into daylight. We're able to watch an onboard TV monitor, and people, whether it be in pitch black conditions, stand out to us like lighthouses.
Andy, we're going to a car chase. It sounds, I don't know what they're chasing. It's very fast. 99 Channel 2, we're overhead this pursuit.
Slung below the helicopter is a special thermal imaging camera.
Right, get ready for a bailout here.
Instead of seeing light, it sees heat.
Still moving, Dave.
992 units, we've got the bailout, the garage.
High temperatures, like a person's body, look black. The cooler surroundings are shades of grey,
We've got 2 suspects out.
much hotter than their surroundings. Warm hands on a cool wall can also leave their mark. This guy has been sitting in a hot steam room for several minutes. What's going to happen when he steps into a cold shower? The warm yellow becomes a cool blue. We use our skin to feel
At the moment, the police officers, that's 2 of them, that's definitely 2 of them.
So they've got 1 arrest out the other side.
Haven't they? So they've got 3 then?
Yes.
Oh, they've got 4 now. 4 out of 5. 99, that was received. So you've got 4 out of 5. I beg your pardon. In that case, I think we will call that a result and resume.
a job well done thanks to thermal imaging.
Well done.
Being able to see temperature differences makes an ordinary supermarket look completely different. Temperature can help the police catch criminals.
We have a system on board the aircraft called forward-looking infrared. It doesn't come cheap. It's very expensive. But what it does enable us to do is to turn dark